Hi, Peter.
Hi, Jordan. You can hear me now, huh?
Yes, I can.
Good.
I'm glad to meet you. Glad you made it.
Thank you. So let me first quickly see. Sharing screen should not be a problem, but let me just try it.
Perfect. Let's see.
Okay.
Okay, that looks good to me.
It looks good, huh?
Yeah, perfect.
Good. Very good. Stop sharing. Okay, so
yeah, so I'll give you a brief introduction at 10:30, and then it'll be all yours. And we want to try to wrap up hopefully a little bit before 11:30 because we have another session starting right at 11:30.
So is the other one actually on the same channel, or is it?
So it'll be a separate Zoom link and
Okay.
And the separate live stream.
So if I want to, I've seen it, of course. I mean, there's the panel discussion, right? And I can just go on the YouTube channel there, right?
Yeah, that's right. So the Zoom link's just for internal to Purdue, but yeah, you'll be welcome to join on YouTube as well. And if you have any comments, we'll be watching the chat, so we'll make sure that we see them as well.
Good. Yeah. So you're at home, I guess, if I look, or are
yes.
you?
Yeah, today I am. I kind of am like half and half. I go to the office some days I stay home.
And teaching, is it in person or is it, how does that work?
This semester, we're mostly in person. So I'm teaching one class. So I like that better. I'm glad that we're.
Yeah, sure. It's much better. Yeah, I mean, it's me too. So it's so actually we just started the semester this week. And all the lectures which we give in person, or most of them, there's an automatic camera in the background running. And so students, if they want, they can watch it, but they cannot interact. So it's not a Zoom session or so. It's just
okay.
So, well,
yeah, we have a few rooms set up like that, but not all of them. So it's kind of a case by case on how well we can do the hybrid setup.
So when did you start at Purdue?
This is my second year, so still pretty new here. But
so you came in the midst of Corona, or what?
Yeah, that's right. It was an interesting time to start.
Yeah, it's interesting and also quite hard, right? I mean, you see all your colleagues only online, and
yeah. Yeah, it's been interesting. I've only met a few of them in person these last few weeks, now that people are starting to come to the office again.
Yeah. Well, I think we're all looking forward that the world hopefully will change a bit again. So it's kind of it's tiring, right? I don't know. I mean, I found it quite tiring.
Much more tiring than in person.
Yeah. Although I must say, I mean, so we have kids, they're adults, and some of them are still studying. For them, it's even much harder, I think, because they spend, dozens of hours listening to lectures and so on. So that makes it really kind of quite hard, I think. But
yeah, I don't think I would do well with online classes as a student. I don't think that's my learning style.
Yeah. I mean, there was no other choice, right?
But yeah. But yeah, I think it's hard for students.
Yeah, I agree. Yeah. So of course, they save a bit time in the morning. So if they're having a small commute, they can stay a bit longer in bed, right? But that's about it. So otherwise, there's no big benefit, and the whole student life is gone, right? I mean, afterwards you chat with people or you have a beer or whatever, right? It's all. So we're looking forward that things are hopefully changing. So that's. So, but is this the first semester you're teaching now in person again? I mean, the first since
in
the
person
pandemic?
it is. I taught one online course last year, but this is my first in person here at Purdue. And yeah, I think it's going pretty well, and yeah, I'm enjoying it much more than the online teaching.
Yeah, it's good.
We've still got a few people coming in.
So people can ask questions on the YouTube channel, or can they? And then how do, I mean, at the end, somehow you moderate the questions, or how does that?
Yeah, so part of this is up to you. Would you prefer people ask questions throughout, or just hold them till the end?
It's probably better at the end.
Okay.
Because,
so then,
but of course, if somebody has a very urgent question, it's fine too.
So yeah, I have the YouTube channel open, so I'm just going to keep track of any questions that appear there, and then I'll just read them to you at the end, and that way we'll make sure we get them all answered. And then yeah, the people on Zoom, they can either write it in the chat and I'll read it, or they can unmute themselves and ask themselves.
So did some of the speakers actually come in person of this distinguished theme seminar? Or
yeah, we just had Professor Don Rubin came to visit us.
Okay.
And all the rest have been online. Yeah, I think, I mean, it's a lot to ask to travel all the way here, and especially
for me, and also, I mean,
that's the nice thing with the the COVID's really opened up a lot of these online options. So we've been able to have people that we normally couldn't really bring all the way here.
We quickly fly over to another continent and then we're back again after 2 hours. That's okay.
All right, well, it's 10:30, so let's get started. So everyone, my name is Jordan Awan. I'm assistant professor of statistics here at Purdue University. Welcome to the final week of the Distinguished Theme Seminar Series on causal inference. Before we begin the seminar, we remind those of you watching on Zoom to please keep your microphone muted at all times, unless you're actively asking a question. And if you're watching on YouTube, you can submit any questions you have in the chat, and we'll forward them to the speaker. It's my pleasure to introduce today's speaker, Professor Peter Buhlmann. Professor Buhlmann is professor of mathematics and statistics and director of Foundations of Data Science at ETH Zurich. His main research interests are in high dimensional and computational statistics, machine learning, causal inference, and interdisciplinary applications in the biomedical field. He received his PhD at ETH Zurich in 1993, and then was a postdoctoral fellow as well as a Neyman assistant professor at UC Berkeley, before he returned to ETH Zurich in 1997 as a professor. He is a fellow of both the Institute of Mathematical Sciences as well as the American Statistical Association. Professor Buhlmann is a highly cited researcher with nearly 40,000 citations and over 200 publications. We are honored to have Professor Buhlmann joining us here today, and let's all give him our full attention.
Okay. Thank you very much for this nice introduction. It's also my great pleasure to be here or there. It's an opportunity, of course, also for me to quickly visit Purdue, and it's my pleasure to do so. So this is again the title of my talk, Statistical Learning, Causal, Oriented, and Robust. And I would first like to acknowledge my main collaborators for the research I'm presenting today. This is Dominik Rothenhäusler at Stanford, Niklas Pfister, University of Copenhagen, Yuanzi Chen, Duke University, Jonas Peters, University of Copenhagen, and my colleague Nikolai Mainshausen at ETH Zurich. Let me start with the topic of statistical machine learning. As we all know, we have nowadays multiple of terabytes of data, a huge amount of data, and we want to extract something useful. We want not just black boxes. We want to understand and get new insight. And some people call this nowadays interpretable AI or interpretable machine learning. And as a statistician, I still would like to call it also interpretable statistical inference in modern context. As I will argue, and as you will see a bit in my presentation, actually better understanding exhibits increased robustness. This is maybe no surprise in vague scientific folklore terms. If we understand a system well, maybe it also works in a robust manner, but this claim needs to be formalized and mathematized, and I will do that a bit, at least in my presentation. In fact, we will show that causality, this is kind of the distinguished theme of the seminar series, causality, and on the other hand, robust prediction, they're closely related. And this is a bit an unusual, but in my view, very fruitful view of the two fields. So let me start with the very basics somehow. If we have data, we think often of a single data generating distribution, and then we do statistical inference. And I'm quoting from Mosteller and Tukey, 1968. One of the hallmarks of the statistically conscious investigator is her or his firm belief that however the survey, experiment, or observational program actually turned out, it could have turned out somewhat differently. Okay, so the statistical paradigm is we have data, we have values, just numbers, and we interpret them as outcomes of random variables. Let's call them Z1, Z2, Zn. And then we model them. Maybe the easiest model is an IID model or a kind of a stationary process. And the underlying model has a data generating distribution, which is denoted by P0. So P0 can be very general, can be infinite dimensional, nonlinear regression or classification, could be also PDE models in mathematical sciences. And the goal is classically inference from data about a function of P0. We all know that, I guess. So the history is very rich on this topic. I go back to Grant and Petty, 1662, and we have a lot of famous people here listed, and there's a huge literature on that problem. Most of this is about generalization to new data from the same distribution as the observed training data. So kind of in folklore terms about a new patient with the same characteristics as in a representative study which has been made. Now, what I want to talk about is generalization to new data generating distributions, and the classical framework does not easily allow to generalize beyond the data generating distribution P0. So my setting is as follows. I have observed data from a data generating distribution P0, and my goal is I want to say something about a new P prime which is different from P0. Now, in general, of course, this is a very ill-posed problem, but people have made progress on this ill-posed problem under the kind of wordings of transfer learning, domain adaptation, transportability, which is kind of quite causal oriented, and so on and so forth. So this is, in a way, my goal. In fact, I want to go a bit more general than this. This is maybe a bit more realistic in practice. Maybe my data doesn't come from a single data generating distribution, but maybe I have various data generating distributions in play. Let's call them PE. And E is a so-called, say, a scenario, a subpopulation, a source, an observed environment. And so in some sense, you can think of, I have access to heterogeneous data from these various data generating distributions. And now I want to say and generalize something beyond what I observed. I want to say something about a new PE prime, where E prime is a scenario which we've never seen in the data set. Same problem somehow, just a bit more general in that I have various sources, various subpopulations of data generating distributions. There are very many examples where this is relevant. For example, multi-center study with diverse subpopulations, but the goal often is to generalize to new, different outside study subpopulations. And I'm quoting here from Dahabre et al. Instead, for decision-making, the users typically have a new target population in mind. I'm also referring to Cox 2001 in his comment to Leo Bryman's famous paper on the two cultures. Cox wrote in his comment, "The success of a theory is best judged from its ability to predict a new context." And so here is my last illustration. This is kind of a cartoon illustration of this problem. This is about an autonomous system. I'm not working in this area, but this is a self-driving car. It's trained on design scenarios from this script D. This is kind of the collection of the observed scenarios which I have. But the point is, you want to say something to generalize to new scenarios, E prime, which you've never observed in the data before. Okay, so that's the issue, generalization to new data generating distributions which you've never seen before. If one ignores the generalization problem to such new generating distributions, in many realistic applications, machine learning algorithms will have very poor performance. This is very well documented. I'm not going into details about this. And I should also say standard machine learning often performs very well on new data from the same distribution P0, which was used for training. Okay, so how can we try to attack this problem to generalize to new data generating distributions? There are various ways to do so, but I'm taking a bit of causal view on this. And let's try to model the entire system, and also let's look at models how these different scenarios actually could have arisen. To make things more clear, I look at a response, a target variable y of interest. I have explanatory variables or features or covariates x, and we must also take into account hidden variables h in the game. So if I would know the true underlying system, it could look like this. So here is my response y. The graph would say it's directly influenced by these x1 and x2. And there's also here a hidden confounding variable h1 here, which could be quite troublesome to do inference on kind of a model from x to y. Okay, so if that is the model, observed are only the observables y, x1, x2, x3, just y and x is observed. And then what you can do is you can look at associations, you can compute correlations, you can look at regression association. And what will happen is you will see typically too many relations. They're spurious because you have omitted the hidden variables. That's one issue. And the other issue is there's typically no directionality if you do so. So you cannot say whether x1 is a cause of y or whether y would be a cause of x1. So the classical goal, maybe the main task of causality, would be the following aim. We want to infer the true relations and the directionality between the observables, between x, j's, and y. This is a very ambitious goal. It's very hard to do, at least with kind of non-designed experiments. And clearly it cannot be solved by regression or standard machine learning techniques. You cannot easily find that directionality, and it's also hard to deal with these hidden confounding variables. So this would be kind of the main task of causality. It's very ambitious. Maybe we can look at a less ambitious goal and just say, let's just try to do robust prediction of y from the features, from the covariates x. That's quite classical. But let's do this prediction under perturbations, under interventions for various subpopulations in the system. And the picture just looks like this. I have my features, my covariates x. I want to predict y. And there are the different scenarios, the different subpopulations, which are kind of symbolized here with this node E, the different environments. That is a less ambitious goal. And as we will see, the goals are related to each other. Okay, so how do we formalize this? I use structural equation models. They have been also highlighted in the previous talks in this series. So I have a graph. For simplicity, it's a DAG here, directed acyclic graph. It has a certain structure, and I specify, once I have the structure, I specify the function models for all the random variables in this graph. So the notation is W, it's the collection of all the random variables, Y, then the covariates X, the hidden variables H, and we model all of them, say the J's component, Wj, as a function of the parental variables, comma, error term, and we do this for every variable. So Y is a function of X1, X2, and H1, comma, error term. An important assumption is that these error terms, they're jointly independent. Now, Judea Pearl calls these structural causal models, and there's a philosophical step here by assuming that this kind of model captures true underlying causality. This is fine, this is good, of course. I'm a bit less philosophical, and I just call these structural equation models. Mathematically, it's exactly the same. So here's the first important remark. The experts, of course, know this, that learning the structure, the DAG, just say from observational data, it's impossible in general without additional assumptions. You can only estimate the Markov equivalence class of graphs. This is very well researched and documented. And kind of in ordinary words, this means learning directions, learning causal relations is very troublesome if you have only observational data at hand. Okay, so why do I introduce these structural equation models? And then I say, well, it's very hard to learn the graph from the data. I think it's very important to use them as a model for perturbations, for interventions, for scenarios. And I want to give you just the example of Pearl's 2 intervention. This is just one example, one simple example, and then I'll move on from there. So these structural equation models can be very useful to model what an intervention could mean. Now here's a little example. Here are my random variables, my graph. Here's my structural equation model. So for example, y is a direct function of x2 and x1, comma, error term. Now we make an intervention at the second variable here, x2, and the intervention says, let's set x2 to a numerical value, little x. You set it to little x. This is an external intervention. Hence, the dependence of x3 breaks. You delete this arrow here. And then you write down the structural equation for this graph, which is here. And the point is, the structural equations remain the same. There's the same f1, the same fy function. But I set the value of this random variable x2 just to little x. So this is interesting because it's dynamic propagation of interventions. So this value little x propagates to x1, and then through x1 it propagates to y, and it goes also directly to y. So it dynamically propagates through the order which is given by the graph. And the other main point, and this is actually a main assumption, I assume that I have the same functions in the structural equation if I do this intervention. This is actually quite a huge assumption. Now, this is a model, right? It's important to point out this is a model for an intervention. It's a very simple, very convincing model. There are many other perturbation intervention models based on structural equations. One can look at additive shifts and so on and so forth. I'm not going into detail about it, but all of them exhibit the following. The first point is they do dynamic propagation of interventions. If you intervene somewhere in the system, it dynamically propagates through according to the order which is given by the graph. And the second part is this huge autonomy assumption that if you do this intervention, actually the structural equations, they remain the same. This is a huge assumption, but you need such kind of an assumption to do extrapolation on something you've never seen in the data. Okay, now we can talk about causal thinking for generalization. If you have such perturbation models at hand, I can use causality to give a prediction, a quantitative answer to a question, what would happen if I perturb? What if I do this and this, what is the prediction in this system? And the point is the perturbation, the new situation is not observed. I can play this game on my computer, right? What would happen if I intervene here or there? This has also been nicely framed out in a very nice framework by Judea Pearl and many others. I refer to him and his book because I think this is a very comprehensive way to think about causality, which gives a prediction to a what if I do question. Many modern applications are faced with such prediction tasks. For example, in genomics, you could ask the question, what would be the effect of knocking down the activity of a gene, say on the growth rate of a plant, and you want to predict this knockout effect without having any data on such a gene manipulation. Same in advertising in e-commerce. What would happen if I show somebody an ad on social media? What would happen if I implement a certain policy, and so on and so forth? So therefore, causality can be used to generalize to new scenarios. This is what I want. What would happen to a new patient who is different, who is a perturbed version from the ones I've seen in this study? So here is kind of another toy illustration to show very clearly that predicting interventions is very different from what we're used to. So the point is, let's try to predict an intervention effect. This is synthetic data. I have YX data. I can fit a regression line. It fits well. It's simulated data. And now I make an intervention at the X variable. I set X to the value -8. And the question is, what is the prediction for Y if I manipulate X to -8? If you look at that, in textbooks, we would read, okay, the best prediction is on the regression line. And that is the right answer if X causes Y, if X influences Y, because if I manipulate X, something happens to Y, and what happens to Y is described by this regression line. Now, you could also argue, well, if it goes the other way around, if Y would influence X, if I manipulate X, nothing happens to Y, and the best prediction then would just be the mean of Y. And that is the correct answer in this picture. And so the challenge is actually, how can you make the right prediction if you manipulate at X equals -8? Okay, so this is synthetic data, but this is actually real stuff. So this is what we have been working on in predicting gene knockout experiments. So what you see here are scatter plots of two genes. It's a very high dimensional problem. I just pick an X gene and a Y gene. I plot the gene expressions. And what you see here is the blue data cloud. And you see also an estimated regression line. It all plays up here. Then what people did in the lab, they did an intervention at the X gene. It had a huge effect. This is not a log scale, so you essentially push expression to 0. So it has a huge effect if you do the intervention at X. And lo and behold, Y changed roughly according to the estimated regression line here. Now here's another XY gene pair. This is the observed data. You can fit a regression line. You manipulate. People in the lab knocked out the X gene. So the activity goes down and nothing happens to the Y gene. And of course, this is exactly the same problem as before. The challenge is how can you predict when you make an intervention at a gene, whether it has an effect on another one. And I will explain that a bit more with some results later, that we can predict that to a certain extent. Okay, so this is a short intermediate summary. Conceptually, if we have a causal or a structural equation model, and if I have an intervention model, it's a model for the interventions, then I can predict what happens when I do interventions. And what I want to go now and do is I want to go backwards. And this will be the next part of my presentation. Let's try to say or solve or address if I observe unspecific interventions from different scenarios, different subpopulations, can I infer back to the causality or at least enhance robustness? Okay, so this is the topic which comes next now: heterogeneity, robustness, and a bit of causality. So I assume heterogeneous data, as I kind of indicated before, from different known observed, let's call it environments, experimental conditions, or perturbations, or subpopulations. This is always indexed with a little e in this space, script E of observed experimental conditions, observed subpopulations. I'm having a regression classification type problem. I have covariates, I have a response, it has a distribution, and it all depends on the subpopulation or on the environment. So examples, to just make it clear again, I could have data from 10 different countries. So my 10 different countries are 10 different subpopulations, and the E, the script E, would be the labels 1, 2, up to 10. Or I could have medical data from 13 different centers, hospitals, and so on and so forth. So now comes the next step. Now I consider many possible but mostly non-observed environments, perturbations, scenarios. They are from a space script F, which is typically much, much larger than the space of observed environments, observed perturbations. Examples for this script F, well, I could have the 10 countries from where I have data, and maybe all other countries in the world, which I've never seen in the data set, or the 13 centers or hospitals, and many new ones which I've never seen in the data set. And the problem is here a prediction problem. Just predict Y given X such that the prediction works well, is robust for these many possible new environments, E in this much larger space script F, based on data from much fewer environments from script, on new data generating distributions, that coming back to the out of data generalization issue. Again, this is the problem. I want to predict Y given X such that it is robust across all these future perturbations. And let's try to formalize this a bit. For example, I just look at linear models mostly in this presentation. We can formalize this. Let's try to find the regression parameter which optimizes a worst case squared error loss or risk over all perturbations or scenarios in this script F, which I have not seen in the data. So people would call this robustness, right? You want to optimize such that you are based on the worst case risk. Maybe worst case is a bit conservative, but we can do this. But this is also causality because it deals with the issue, what happens in a new scenario, which I've never seen in the data. And now I want to make this a bit more clear. Causality and worst case risk over scenarios, over perturbations are actually related with each other. Again, for linear models, in a nutshell, this is maybe one of the main results in the talk, and I'll make it a bit more clear technically later. But actually, it's true if I optimize worst case risk over a certain class of perturbation models, of intervention models, this gives me the causal parameter. And of course, it all depends what this script F is. What is the model for the future perturbations, for the future scenarios? But the interesting point is that risk optimization all of a sudden is the same as causality, at least in this framework. So let's expand a bit on this result. So again, in a nutshell, without going into technicalities, if I look at perturbation models, this script F, intervention models, which allow for all perturbations which do not act directly on Y, but they dynamically propagate, as indicated earlier. So here's kind of a picture. I have X, I have Y. There's an underlying internal systems parameter or a causal parameter, and I have perturbations, environments. They act on X, but they do not act directly on Y. Then this result is true, that worst case risk optimization equals the causal parameter. Say in a linear system, in a linear structural equation model, this causal parameter beta 0 is the regression parameter if I regress on the parental variables of Y. So this is quite interesting. This can be expanded. I think the experts know that this even holds under hidden variables in the game. And I'll come back a bit to this later. But the point is, worst case risk optimization and causality indeed are closely related to each other. Causality and this distributional robustness are intrinsically related. And I put here a picture of Trygve Havelmo. So Havelmo kind of wrote this in 1943, of course, in different language, but here is again the translation. I'm coming to that. I should just point out Havelmo is a famous person in economics who later got the Nobel Prize in 1989. So Havelmo actually derived an invariance principle. And in my language, it reads as follows in linear models. If you take the causal parameter, the causal solution, and you look at the residuals, if you use the causal parameter, and you look at the distribution of the residual, then this distribution is invariant, is the same across all perturbations in this space script F, which do not act directly on Y. So this is really what Havelmo has seen very early, that causality leads to invariance of residual distributions. So this is Havelmo. Causal leads to invariance. And a couple of years ago, we advocated to say, hey, we can invert this process. Let's try to observe invariance in the data and then infer causality. And just in a nutshell, do or propose is as follows. We search by statistical testing for a parameter, let's call it beta star, such that the residual distribution of beta star when using beta star is the same across all subpopulations, across all environments which you have seen in the data. You can do this with linear models. It's not too hard to do. And one can prove that if the different subpopulations, the different scenarios which you have in the data, if you have sufficiently many of them, and if they're sufficiently rich, then at some point, this beta star actually gives you the causal parameter. Of course, there are assumptions underneath there, and I'm skipping them, but the point is, if you have enough observed rather unspecific interventions in the data, indeed, you can infer back to causality. This inverted process, we call this invariant causal prediction, ICP. It's a statistical method. It has error control under some statements like the probability of having at least one false positive claim, that we claim causality and actually it's not, can be bounded by alpha like 0.05. I'm skipping the technicalities here because I will explain it a bit from another angle, but I want to point out that this actually has led to quite interesting findings in these gene knockout experiments. And let me just briefly explain you a bit what we did here. So we have genome-wide mRNA expressions in yeast, a bit more than 6,000 genes which are involved. We have quite a few observational samples of wild-type yeast, 160. And the people in the lab, they knocked out already single genes. Actually, 1,479 single genes have been knocked out. Okay, so what do we do roughly with this data? We fit an invariant linear model of one gene versus all others. This is a high-dimensional model. And then we rank the genes according to p-values for invariance. So it is possible to get these p-values for invariance. And we say this is the most invariant gene, the second most invariant gene, and so on and so forth. And so what we essentially exploit is that the observed gene knockouts, we have more than 1,479 observed gene knockouts. They're different scenarios, different environments. They are used to predict new gene knockouts, which you've never seen in the data. You can validate this. You put a third of the interventional data aside, and you try to predict it. And if you do so, you come up with this ROC type curve. So on the x-axis, there are the number of the prioritized predictions. This is the most invariant gene, the second most invariant gene. And on the y-axis is the number of true strong intervention effects. So we're trying to make this prediction. If I knock out the X gene, does something happen to the Y gene? So I actually exactly try to address this problem. And if you use this invariant linear model fitting, this ICP procedure, this is the red line here. The kind of surprising thing is that the first top 5 predictions, 1, 2, 3, 4, 5, the first 5, they're all leading to true predictions of the interventions. The 6th is not, the 7th is true, the 8th is not, the 9th is true, and then it levels off. And these are other methods. They're a bit worse. Here's a related method. Well, at least the first 5 you could predict correctly. This is not very many among 6,000, right? Or among the remaining 4,000, whatever. But it is a very hard problem. So it was interesting that we could validate this to a certain extent, but it's a super hard problem. It's a very noisy problem, and the problem itself is difficult because you really want to do this prediction. So I would not claim that these are causal genes, but I would say this kind of causal inspired view and invariance helps us to prioritize future next experiments. Okay, so let me kind of make this a bit more formal, what I try to explain. I try to convey that kind of going for invariance across different environments, across different subpopulations is a good principle, inspired by Havelmo's result. And let's now try to do this in kind of just a regularization way. So we want to encourage various degree of invariance from small to large. So in essence, I try to make the residual distribution constant. Maybe I don't want to make it exactly constant over my observed environments, but I want to make it fairly constant. So the environments E, the subpopulations, which I introduced before in the talk, I now denote them as outcomes of a q-dimensional random variable A, and I call this an anchor. You'll see them in it Y. So just make the switch notationally from E, this environment, they are outcomes of this A variable. And what you could try to do is to say, okay, let's try to fit the regression parameter to minimize residual sum of squares, but you regularize towards solutions such that the inner product of A with the residuals is kind of not too large, so that the correlation between the residual and say the environments are not too large. So this encourages correlation invariance. So this is kind of maybe a first proposal. It's not quite what we propose under the name of causal regularization. What we actually propose is something related to this. We look at this projection operator, just a linear projection onto the column space of A of these environment or anchor variables. And then we propose to say, okay, we minimize residuals, we minimize over beta, and I minimize the anti-projection residual length squared, plus here's a regularization parameter gamma times the projection residual length squared. For gamma equals 1, this is least squares. This is Pythagoras, right? I can always decompose square area in anti-projection and projection length squared. And for general values of gamma, this is what we call general causal regularization. If you're in a high-dimensional problem, you can add an L1 norm penalty, another sparsity enforcing penalty. All this is very simple to solve. All this is simply a convex optimization problem. The framework also encompasses nonlinear function estimation. So you can also try to fit nonlinear functions, random forests. I tried this actually, neural networks. I didn't try this, but with random forests, I did try it. And you just optimize anti-projection residual length squared plus regularization parameter times projection residual length squared. So you can add this form of invariance to a broad class of models. And perhaps in some applications, one should do this. The question is, well, what is it actually doing if you do this? And this is what I want to expand a bit on this. So here for simplicity, again, for linear models, I have X, I have Y, I have maybe a causal internal systems parameter beta 0, I have hidden confounders, and I have these anchor variables, these different environments. And the question is, how do these variables act on the system? If it goes this way, if they act directly on X, but not on H and Y, this is the instrumental variables regression model. This is a very popular, well-known model in economics, econometrics. And it has this one huge assumption that the instruments, that's what they call it, I call it an anchor, my environments, they are not allowed to directly act on Y, and they are not allowed to directly act on H. And in particular, this assumption that is not allowed to act on H is kind of a big assumption, because I cannot even name what H is. So it's very hard to kind of try to validate or justify this assumption. So we relax this. We say, okay, this variable is allowed to act on Y directly also on H. We also allow feedback loops, so the arrows can go in all directions. The only assumption which we make here is that A is a source node in the graph. And that explains the name anchor. A is an anchor node in the graph. And then we propose this, what we call anchor regression. So this is now a quantitative model on this graph. It's just a linear structural equation model of the X, Y, and the hidden variables. It's linear plus error term, and then comes this exogenous part from the different environments from these anchor variables n times A. So we allow that A acts on Y and H, and that is a problem. So people say, well, then you cannot identify the causal parameter. And that's true. That's the price you pay for relaxing this assumption. So that's maybe why people say, well, this is forbidden to do. If you do that, this causal regularization in this anchor regression model, it still solves for optimizing a worst case risk problem for a certain class of perturbation scriptive. So I'm now pulling back to the robustness viewpoint. And let me explain this just quickly. So in this anchor regression, I have a linear structural equation model here, an error term. I have a term from the exogenous variables, m times a. This corresponds to the different environments from before. And now I define a model for perturbations, for new scenarios, and I call them shift perturbations. And what we do is we say, okay, this exogenous term is replaced by a vector v. V is random or deterministic. This perturbation propagates through all the structural equations, as I indicated before. We have the same parameter b here from the data and from kind of the perturbed version. And there are two important points about this perturbation vector v. V is in a certain space C gamma. Here's the technical definition, but one should keep in mind, or I want to point out that gamma essentially measures the size of V in L2 norm. So if the perturbation is strong, then gamma is large. The other point is that V is not allowed to go in arbitrary directions. It must be in my model within the span of M. So here's again this technical definition, but it's important that it's in span of M. So in folklore, if I try to translate what we're doing here, we're saying, okay, our perturbations V are modeled in the new test data that they must have the same direction, namely span of M, as the observed heterogeneity perturbations in the training data. So you see heterogeneous data, you observe it, you see certain directions, and now we say, okay, the future goes along these directions, but could be much stronger. Well, this is maybe the most natural extrapolation. How the heck would you want to extrapolate otherwise? And the other point is the more perturbation and heterogeneity you see, the better you can extrapolate. Why? Because the span of M becomes larger. And this is somewhat controversial in classical statistics, but it actually has fundamental consequences for robustness. If you see more, even unspecific interventions, at least in this framework, that's good. It allows you to identify more. So here is actually a fundamental duality theorem. And I just explain that in the population version. We have finite sample version in the paper. And so this pi A, this projection operator on the column space of A, becomes now just the conditional expectation. And I denote it by P of A. And the theorem reads as follows. For any regression parameter beta, you can look at worst case risk over these perturbations, which I just defined, these shift perturbations in this anchor regression model. So V is in this C gamma. And the theorem says this worst case risk is exactly equal to the objective function of my causal regularization, namely anti-projection residual length squared plus gamma. And gamma, this regularization parameter, is actually corresponding to the length of the perturbation plus gamma times the expected value of projection residual length squared. So this theorem says worst case shift interventions, they correspond to regularization. And so the left-hand side is actually difficult to do. The right-hand side is super easy to do. I showed you how you can even introduce lasso penalties and so on and so forth. So robustness corresponds to causal regularization. So this is the result, right? And I show here a couple names and pictures. On the left-hand side, we have the robustness world, kind of statistical robustness, distributional optimization robustness, adversarial robustness, and here also some renowned people from the causality world. These things somehow are connected to each other, at least in the framework which we're presenting today. So what is the difference? Quite an important point. Robustness actually looks at problems like this. I look at worst case risk, say L2, and I have reference distribution P0, maybe my observed empirical distribution, and then I want to be robust across all distributions which are within a ball of radius rho in a certain metric. So in robustness, we postulate a metric like F divergence, Wasserstein, and so on and so forth. And then you choose a radius rho, and then you want to be robust here. Now, this causal regularization framework is related, but it's a bit different. The metric actually is kind of an ellipsoid metric, which is learned from the observed intervention of the observed perturbation data. I see some sort of heterogeneous data already, and that gives me my span of M, and that gives me the geometric directions where I want to robustify. And this gamma parameter corresponds to this rho radius here. So the point is, what we do is we learn actually the metric from heterogeneous perturbation data, and this can be particularly important when the dimensions are high. It's kind of hard to postulate maybe a metric which is good in applications, but if I already have some sort of heterogeneous data access, I have a chance to estimate maybe a better metric. In view of time, I'm not saying much about this. Actually, it's known that one can improve prediction with this kind of causal regularization scheme. It doesn't always work, but people have reported some progress on it. It has also been debated, but at least we have a clue and understand it when this causal regularization works and when it doesn't work. Namely, it does work when kind of the future perturbations are in this span of M and reality might be different, and then it doesn't work. I have actually somehow more interest maybe in the interpretation. And as we all know, science aims for causal understanding. This may be a bit ambitious without having very nicely designed or randomized studies. In that case, it's possible, but if I just have a bag of data, causal inference necessarily requires often untestable assumptions. Like in my anchor regression model, if this is the case, I cannot identify my beta zero. But let's go back to this causal regularization, and let's just look at the problem and say, what happens if this causal regularization parameter gamma is chosen to be very large? So I can look at beta gamma. This is the parameter. This is kind of like in the population world, this is a parameter. Depending on how I choose gamma, and if I push gamma to infinity, I have a parameter which I denote by beta infinity. And by this fundamental duality, under these shift perturbations, one can easily prove that the residual with this beta infinity remains invariant over shift perturbations. That is, beta infinity is not the causal parameter, unless, say, we are in an IV, instrumental variables model, where the conditions hold, then it's the same. But because of this shift invariance, let's go back to Havelmo, it's still related to causality, and we call it diluted causal. And so I want to show you this picture of notions of associations and where we are and what we're actually in some sense trying to do. Maybe the simplest notion of association is marginal correlation. That's the yellow world. Then you can go one step further. You can go to regression, association, partial correlations. That's the green world. And we want to push this further and say, well, we want to go to invariance, association, which leads to invariance. And at the inner ball here would be the causal association, which is very hard to get from sort of non-designed studies. So this is actually stabilizing, and actually Peng Ding, he pointed me to this work of John Tukey, and I'm quoting here Tukey in 1954. One of the major arguments for regression instead of correlation is potential stability. He doesn't talk about partial correlations, so it's potential stability. We're very sure that the correlation cannot remain the same over a wide range of situations, scenarios, subpopulations. but it is possible that the regression coefficient might. We're seeking stability of our coefficients so that we can hope to give them theoretical significance. So what we do is how to stabilize further from yellow to green. That's tricky. And now we go from green to blue to stabilize further to invariance. And maybe for the last very few minutes of my talk, let me just show you a bit how we use this kind of diluted causality in an applied project. So finding important proteins for cholesterol. This is a collaboration with Rudi Ebersold from ETH Zurich. So he's a very renowned expert on proteomics. Here is a cartoon illustration of the cholesterol pathway. It contains a couple genes, proteins. So Ebersold's lab can measure the protein abundances here in the cholesterol pathway, and it can also measure many other proteins outside the cholesterol pathway. So it's measured in an experiment with mice. There are two environments, two scenarios. Some of the mice, they get a low-fat diet, and the other one get a real fatty diet. This probably happens something on the cholesterol if you look at the difference here. And then we run high dimensional regression. Total sample size is 270. Why? Is the cholesterol pathway activity. It's kind of like the first principal component of the cholesterol abundances in this pathway. And the covariates are all other protein expressions. Okay, so here is kind of the result. Now you can look at, okay, you run high dimensional regression, let's run lasso, and let's look at importance of different proteins for the cholesterol pathway. And that is in essence plotted on the x-axis. So this is an importance measure for single covariates, for single proteins, but actually the ones who are strongly regression associated, but not invariant. So they're here. And on the y-axis, you look at importance with respect to invariance, and you see a bit of difference. And so our approach is to say, okay, these are the more important players for the cholesterol pathway than the ones which come from regression. Now you can ask, well, does this work? And of course, it's hard to validate, but we do validate this in various biological systems and pathways with proteomics and with transcriptomics. And in a nutshell, what we find is invariance, this kind of notion of invariance importance is better than just regression importance. I'm not making the claim in general, but in the pathways we have been looking at, we could see quite a bit of gain by looking at invariance. The story would go on. So we have applications also in genomics about distributional replicability. My co-authors have also looked at metabolomics in large-scale kinetic systems, besides what I indicated a bit. Let me conclude. Interpretation and causality and robustness, they're related to each other, at least in the outlined framework, which I've shown you today. The second point is that stabilizing and finding suitable invariances in large data sets is a powerful thing and can make a relevant difference in practice in the context of many models, mathematical models. And my last point is we hear nowadays quite often about causal AI. And this is maybe sometimes a bit an overly ambitious wording, and true causality is perhaps still far away. But in fact, if you look what causal AI papers do and contributions do, it is mostly about robust and reliable prediction. Thank you very much.
Great. We have time for a few questions. So some in the chat. In the first example with genes, we have a question is, when there are so many genes, how do we measure the intervention effect of each gene?
Okay, this is an interesting point. So we can only measure the intervention effect of each gene on another one with this interventional data. And so what we actually do is, so we have the observational data, you have this intervention. It's a bit like in my picture, and you see, okay, the intervention did something. That's the first point. And the second one is if the effect on the other, on the Y gene is, and that's how we defined it, if it is outside the data range which you observed, then we call it a true intervention effect. We don't quantify it's a strong effect or not. We just say it is a strong effect or not, and we define it to be a strong effect if actually the intervention pushed, say, the expression of the Y gene outside the data range which you observed.
Okay. The next question is, when we were talking with the connection to robust optimization, how is script F determined? And can you comment on how the solution of the robust optimization problem varies if you have the wrong choice of script F?
Okay, that's a good point. I mean, so what one can do, and we have not written it up yet or kind of somewhere in the drawer, I mean, in easy cases, we can look at, say, Gaussian models. And then you can look at these perturbations, like these shift perturbations in the anchor regression model. And in the Gaussian case, what it means is that it is Wasserstein distance between Gaussians. If you look at the Wasserstein distance between Gaussians, it is the covariance which determines that. And so you can actually write down an explicit expression of this V perturbation vector and how the covariance matrix changes. And it is kind of like a bit in this picture that it becomes, instead of a ball, if you think geometrically, it becomes an ellipsoid. And we understand how from the ball it goes to the ellipsoid. We can do this in the Gaussian world where there's sigma, and then we can kind of characterize that. Outside the Gaussian world, we don't know how this should be done, how the solution. Well, the wrong choice of F is kind of like the same as the wrong choice of my metric in my robust optimization. So this is, of course, an interesting point, but if I have the wrong metric or the wrong perturbation model, mathematically, I have no clue what happens. I cannot say much. From a practical point of view, maybe you still hope that you capture some of the robustness, but maybe not everything.
Okay, maybe we'll do one last question from YouTube. We have the question is they say the connection between causality and invariance is very interesting. How about the case with heterogeneous causal effect under which causality is not necessarily invariant?
Yeah, that is an interesting point. So I think the heterogeneous causal effect is typically in terms of X's, right? Like different covariates of a certain patient and so on. I think one could put on top of this, one could put different studies, different external perturbations. The invariance here, that's maybe an important remark. The invariance is anchor variable. It really has to be exogenous. It had to come external. And so if you put that on top of heterogeneous causality, it could give you an additional handle to determine whether X causes Y or Y causes X. So far as I understand it, like also the nice work by Susan Athy and Stefan Wager, is that, okay, you know that X heterogeneity, you know that the treatment and the outcome given X are randomized. And now you can, of course, play around this and say, well, if you have maybe additional hidden variables, or if you have kind of directions of X which you want to include in the model, then you can put additional invariance to that model. We haven't done that, but I think in principle it's possible. But it's not the same. So heterogeneous causal effects are kind of trying to understand the personalized causal effect.
Okay. All right. Well, I think we're gonna have to wrap up here. So thanks again for joining us, giving a really great talk.
Yep.
Peter,
thank you so much. This is really appreciate. Wonderful talk.
Thank you.
For your time. I understand you're from different time zone, but thank you so much. I really appreciate.
Well, it was my pleasure.
Great job.
Okay. Thank you. Okay.
So right now we have another session, panel chaired by Professor Jun Xie, where we'll discuss what we've learned through the seminar series. The panel is in a separate Zoom meeting and a separate live stream. Both are live right now, so we can all head over there. I hope to see you all there shortly. And let's thank Professor Buhlmann again one last time.
Thank you, Peter. We appreciate it. Hope we come to visit in person sometime in the near future.
Okay, I'm glad to do so. I'll let you know when I'm coming closer.
Sure.